So yesterday we had a brief introduction to the things that we're going to be covering. So those were the laws of thermodynamics. Okay, so we're going to start today with a few definitions or some terminology that we're going to need. And then after that, we can look at the laws and then properly understand them because we know what the words mean. Okay, so the first thing is looking at a thermodynamic system. Okay, so imagine we have a large system of particles, for example. Okay, so we've got this large system over here, and there are particles around. Okay, so that's a system of particles. A thermodynamic system is a portion of this large system that we are interested in. Okay, so it's up to us to define which region of this whole system is the one that we're going to call our system. Okay, so let's say we block off this amount here, and we say this is going to be our system. Okay, once we've defined the boundaries for our thermodynamic system, everything else we refer to as the environment. So physically, there might not be much of a difference between our system and the environment because it's all together in the same place. However, this predefined boundary that we set, that is what we use to separate our system from the environment. In the next section of the module, this environment is going to be kept at a fixed temperature T. And since it is much larger than our system, this larger environment at a fixed temperature will fix the temperature of our system. And in that case, we call the environment a heat bath. Okay, so it's like a large body at a fixed temperature, and it fixes the temperature of our system that we predefined. Okay, so that's what we mean by a thermodynamic system. Okay, now as physicists, we like to classify things. So we classify or label, however you want to think about it, a system. Okay, now when I say system, I mean thermodynamic system. Okay, so we know what that means now. So we classify a system by what is allowed and not allowed through interactions. Okay, so what do I mean by interactions? I mean the interactions between the subsystem that we're calling our thermodynamic system and the environment. Okay, and there are two ways for these two systems to interact with each other. So the first way is through particle exchange. Okay, so we've got our system, we've got the environment, and maybe particles are being exchanged between the two. For example, if this was a room full of gas and we've got a little meter cubed box, just imagine a meter cubed box inside the room. If we call that our thermodynamic system, there's nothing stopping gas particles moving into our box and moving out. Okay, because it's just an imaginary box that we're making. Okay, so that's called particle exchange. We could also have energy exchange. Okay, so through particle exchange or any energy exchange, the subsystem is interacting with the environment. Okay, and depending on whether these types of interactions are allowed or not allowed, we can classify our subsystem. Okay, so how do we classify them? We've got the type of system. So this is our classification. Okay, and then there are several things that we allow or not allow. The first one is mass transfer. The next one is work. So we all know what work is. If I push on something, I'm doing work. If something pushes on me, then that thing is doing work, right? Basically, force times displacement. And heat transfer. Okay, so we still don't know what heat is, but we will get to that. Okay, one step at a time. So the type of systems can be open, closed, thermally isolated, okay, or we might say insulated. Okay, so like if you are insulating your house, you are trying to make it thermally isolated. So if it's cold outside, the inside stays warm, for example. Or if you want the insides to be cold, if the outside is hot, then the inside remains cold. Okay, it's insulated thermally. Okay, then we can have mechanically isolated. And we can have just isolated. Okay, so there's a difference between thermally isolated, mechanically isolated, and then just isolated. Okay, so let's just put in our columns here and rows. Okay, so for an open system, we allow mass transfer, we allow work to be done both ways, and we allow heat transfer. Okay, so all three are allowed. We call it an open system. For a closed system, we do not allow mass transfer, but we do allow work and we do allow heat. For a thermally isolated system, we do not allow mass transfer, we do allow work to be done, but we do not allow heat to be transferred. Of course, because if it's thermally isolated, we don't want it to be getting hotter or colder. We want it to be at its temperature. We don't want the environment to affect it like that. Okay, mechanically isolated, we do not allow mass transfer, we do not allow work to be done, but we do allow heat transfer. So you can think mechanically being pushing and pulling. In that case, work is going to be done if you push something or pull against something. So if it's mechanically isolated, we do not allow work to be done both ways, right? The system or the environment. And if it's just isolated, so no prefix of thermally or mechanically, then we do not allow mass transfer, we do not allow work done, and we do not allow heat to be transferred. Okay, so this way we can identify the type of system based on its interactions. Okay, so that's the classification we're going to be using. And from now on, we're only going to be interested in closed systems. Okay, so we're going to start off looking at closed systems where mass is not transferred, so we don't have any particle exchange. Later on, when we look at something called the Gibbs free energy, we will see that in those cases, mass can be transferred or particles can be exchanged. Okay, and in the next part of the module, you'll also be looking at open systems where particles can be exchanged. Okay, so we're going to start off with these closed systems, and then we can add restrictions. So we can say we're going to look at systems where work can't be done. In that case, it's going to be mechanically isolated, or systems where heat can't be transferred. In that case, thermally isolated systems, or maybe we don't want any transfer. Then it's going to be isolated. Okay, but this closed system, that's going to be our starting point. So from now on, if I mention a system, we know that it's going to be a closed system. implicitly. Okay, but I will try make things as explicit as possible so there's no confusion. Okay, so that's the classification, and then we have a little definition. Okay, and that is adiabatic. Okay, so we need to add this to our list of terminology and vocabulary. So adiabatic means that there is no thermal interaction. Okay, so new word, and we see that we've got three variations of the same thing now. So thermally isolated, insulated, and adiabatic. Those three mean the same thing. Okay, so thermally isolated, insulated, and adiabatic. All three mean that there's no thermal interaction. Okay, so it would be nice if we just had one word for it, but we're stuck with these three. Okay, so if I mention any of those three, we all know it means no thermal interaction. Okay, any questions so far? Okay, so not too bad. So we know what a thermodynamic system is, and we know how to classify one if I give you a system. Okay, let's look at the next chapter or subchapter, thermodynamic variables. Okay, so first of all, what is a thermodynamic variable? So definition. A thermodynamic variable is an observable / measurable property of a thermodynamic system. Okay, so as we see here, we are going to be adding more and more stuff as we go through. So we know what a thermodynamic system is now. Given a thermodynamic system, the observables of the system are called thermodynamic variables. So that can be things like pressure, density, temperature, energy density, mass, number of particles, anything like that. Anything observable of the system, we call that a thermodynamic variable. I've got a question here. Hi, in Dr. Alan Matthews' video, it mentions that for mechanical energy transfer allowed. Sorry, what's this? Transfer allows work to transfer, and for thermal energy transfer allows heat. Yeah, so mechanical energy transfer is just work being done. So if we go back here, this work. So here we just specify for mechanically isolated that work can't be done, but then heat can be transferred. Okay, so we'll see later on in certain cases where this changes. But for now, we're just going to view mechanically isolated as work can't be done, but then heat can be exchanged. For example, if you just have one box and another box, if this has some temperature T hot and this has some temperature T cold, depending on this boundary here, we can allow heat to flow through. So no work is being done, nothing's being pushed or pulled, however, heat is still being transferred. So in this case, we call it mechanically isolated. Okay, and then thermally isolated, that's just like you can imagine, insulating your house. You have some, like something like this. Okay, so you can have a boundary that doesn't allow heat transfer. Okay, however, that boundary, for example, could be flexible, and then it can move back and forth. So work can be done, but then heat can't be transferred. Later on, we'll see the subtleties involved with this transfer. So doing work on something might not always transfer heat. Sometimes it does transfer heat. We'll look at that later on. Okay, but for now, this table is fine the way it is. Okay, so a thermodynamic variable is an observable / measurable property of a thermodynamic system. Okay, so we can break these thermodynamic variables up into two classes. We can have intensive, and we can have extensive. Okay, so I'll just provide some examples of these. So intensive variables are things like pressure, density, temperature, and energy density. Okay, not energy, it must be energy density. Okay, and as with all density type variables, it's going to be the energy divided by the volume. Like mass density is mass divided by volume, energy density is energy divided by volume. Okay, and some examples of extensive variables are mass, the number of particles, volume, and energy. Okay, so the easiest way to tell these apart is that extensive variables scale with system size. Okay, so that's the way to identify extensive variables. If the variable does not scale with the system size, then we call it intensive. In other words, it halves if the system is half, and it doubles if the system is doubled. Okay, so you can think of it like that. So if we just go through the list here, mass, if we double the system size, if everything is uniform, then a doubled system means there's double the mass. Okay, so mass scales with the system size, so it's going to be extensive. Same thing with the number of particles. If you have a box with n particles and you add another box with n particles, so the system size gets doubled, then you have twice as many particles. Okay, for volume, again, if you have a 1 meter cubed box and you add another 1 meter cubed box, you now have 2 meters cubed. So the volume again scales. Same thing with energy. If you have a box with the particles moving around, they've got some kinetic and potential energy. If you imagine 2 of those boxes, then of course the energy doubles. Okay, so in that case, we say that the extensive variables scale with system size. Okay, if that's not the case, then we call it intensive. Is volume considered? Yeah, it's extensive. So if you're confused, just imagine if you doubled your system. So you go from 1 meter cubed to 2 meters cubed, that scaling is double. So the volume doubles when the system is doubled. So it's going to be extensive. Okay, so always just think about adding 2 of your systems together. What remains the same and what gets doubled? Okay, on the other hand, things like intensive, if we look at temperature, if we have one box at 10 degrees Celsius and another box at 10 degrees Celsius, if we put these two boxes together, it's still 10 degrees Celsius. You don't end up with something that is 20 degrees Celsius. Okay, so in that case, it's intensive. Okay, so those are the differences between intensive and extensive. Okay, so now a bit of terminology or a bit more vocabulary on this. Thermodynamic variables are also called, okay, so even more names to go onto this, state variables. Okay, we will see why that makes a bit of sense later on. And they can also be called thermodynamic coordinates. Okay, we will see that later on as well. Just a quick little thing on thermodynamic coordinates. Remember from yesterday when we looked at that PV diagram. So this was the macro state space where each point represents a macro state. You can see that given a macro state, we can coordinatize it using P and V. Okay, so using those thermodynamic variables, we can coordinatize the macro states. Okay, that's why we call it thermodynamic coordinates. So what is state functions? We're not there yet. We will get there. So we're just on thermodynamic variables for now. We'll get to state functions, I think, to next page. Okay, so that's the thermodynamic coordinates. Okay, so the next thing, definition. Thermodynamic variables okay, and we know the other names for thermodynamic variables now are called well-defined if they do not vary from point to point in a system and do not vary in time. Okay, so if that's the case, then we call the thermodynamic variable well-defined. So just as a little example, let's say that we have a block of metal or something like that, and it has a weird density that looks something like this. Okay, so let's say blue means low density. Okay, and then let's say green means high density. Okay, so we've got low density and then something, and in the middle, there's high density. In this case, the thermodynamic variable mass, right? Mass is a thermodynamic variable. It's an extensive variable, is not well defined because we see that if we look across the system, there are some points where there's higher density, some points where there's lower density. So overall, if we look at the mass distribution or the density, this is not well defined, okay, because it varies from point to point. Okay, I've got a question here. Is it wrong to consider them as extensive variables of a system, given system is in equilibrium? Okay, so the idea of intensive variables and extensive variables have nothing to do with equilibrium. Okay, so these variables are defined as is. They're just observables of the system. Later on, we will see that these variables are only well-defined if the system is in equilibrium. So you can talk about mass, you can talk about volume and energy. That's perfectly fine. You can only talk about them being well-defined if the system is in equilibrium. Okay, for example, pressure. You might have the case where you've got a box of gas and the gas is moving around. Okay, so you can still talk about the pressure, but in that case, the pressure is different from place to place. So it's not well-defined. In other words, the system is not in equilibrium. Okay, but there's still pressure. It's just not uniform throughout the system. Okay, so we're going to get to that now. Okay, so for example, this is the density. Rho is not well-defined. Okay. In other words, to be well-defined, the density must be uniform across the system. Must be uniform across the system. Okay, and let's just have a look at the equilibrium since you brought that up. So definition. A system is in equilibrium. Okay, so the system itself is in equilibrium if its thermodynamic variables all of the thermodynamic variables, also known as the macroscopic properties, are well-defined. So individually, all of the thermodynamic variables must be well-defined for the system as a whole to be in equilibrium. Okay, so for example, this system over here, you might have uniform pressure over the thing, you might have uniform pressure, uniform energy, and so on. But since the density is not uniform, the system as a whole is not well-defined. Okay, we need all of the thermodynamic variables to be in equilibrium. Okay, I hope that answers your question there. Okay. Yeah, so some of those variables might be intensive, some of them might be extensive, all of them must be well-defined, and then we can say the system is in equilibrium. Okay, but we have two kinds of equilibrium. So we have internal equilibrium. Okay, so this means constant within the system. Okay, so that's what we were talking about with the density. It must be constant or uniform within the system. Then we say it's in internal equilibrium for all of the inside properties. We also have external equilibrium. So this means constant with respect to the environment. Okay, so for example, for external equilibrium, either we can say we've got a box of gas, we do not allow particles to come in or go out, then it's in external equilibrium with respect to particles, because none are coming in, none are going out, or the same amounts are going in as going out. That's also equilibrium. Okay, because overall it remains constant because just as many are coming in as going out. Okay, so please be careful about that. Also, with regards to temperature, the temperature of the system is the same as the temperature of the environment, then it's in thermal equilibrium. Okay. Okay, and then putting this together, we have something called thermodynamic equilibrium. Okay, so for thermodynamic equilibrium, if you want to understand that, we can break it up into two parts. The thermo part, so no heat flow, right? No temperature changes, so that's the thermo part. Dynamic part, we call that no mechanical work being done. Okay, this means net, right? No net heat flow, no net work being done. And in other words, you don't have this net energy exchange between the system and the environment. In that case, we say that it's in thermodynamic equilibrium. Okay, internal, do you want an example of internal equilibrium? Okay, so an example for internal equilibrium, let's say we've got a gas with a box with gas particles moving around, and there's uniform pressure distribution. Okay, so if you've got a gas that's moving around, it's going to be in the pressure will be internal equilibrium if there's uniform pressure across the gas. So you don't have areas of high pressure or low pressure. In that case, it's going to be in internal equilibrium with respect to pressure. Okay. Okay, so that is equilibrium. And then remember that's split up into two parts. You can have internal equilibrium, so that's constant within the system. External equilibrium, constant with respect to the environment. So same temperature, same pressure, same number of particles in that case. Thermodynamic equilibrium, so we call that a system is in thermodynamic equilibrium if there's no net heat flow across from the system to the environment, so same temperature, and no net mechanical work, okay, to exchange energy that way. If you have those two, we say that it's in thermodynamic equilibrium. Okay, any other questions so far? Okay, just to warn you, I'm using my student Zoom account while the staff one is getting sorted out. So we are limited to 40 minutes. So the time is going to run out soon. When we do get kicked off, I'm just going to restart the meeting, and then please can you just join back? Okay, so I think 2 minutes or something, it's going to turn off. Please just join back after that. Okay, so is everyone okay with the idea of thermodynamic variables and equilibrium? Okay, awesome. Let's have a look at the next bit of vocabulary, and that is a thermodynamic state. Okay, so definition. a thermodynamic state okay, and remember when I say states, I mean macro states. Is a label we give to a collection of microstates that have a common property or properties. Okay, so the collection of microstates that share this common property or properties, we call a thermodynamic state, or the label we give it is a thermodynamic state. Okay, the state, okay, so that's just the shorthand for thermodynamic state, is specified by thermodynamic variables. Okay, also called state variables, as we said before.